Shown in the figure below is a water glass at two different moments. In the first moment, the water glass is empty and the light ray strikes the bottom corner as shown. In the second moment, the light glass has been filled with water of index refraction 1.33. As a result, the light ray has been bent. We are then asked to calculate theta 1, an angle from the first diagram, theta 2, an angle from the second diagram, as well as the distance x as shown in the final diagram. This calculation will involve Snell's law, and Snell's law tells us that when a light ray passes from a first medium with index refraction n1 and an angle of incidence theta 1 and enters a second medium whose index of refraction is n2, it will then have an angle of refraction theta 2. Typically, Snell's law problems are rather easy to solve, and so they are frequently divided into multiple calculations which involve geometrical calculations in between applications of Snell's law. This problem is no deviation from that rule, as Part A involves a simple geometrical calculation. If we look at the figure, we find that the angle theta 1 as drawn is equal to the angle that I have just indicated, and that angle is part of a right triangle that we're highlighting in green. Because two of the sides of this right triangle are known, opposite and adjacent to the angle theta 1, we can find that the tangent of theta 1 is equal to the side opposite divided by the side adjacent. And then solving this equation, we find that theta 1 is 28.07 degrees. In problem B, we are asked to find the angle theta 2, and what we recognize is that the angle theta 2 differs from the angle theta 1 due to the fact that the light ray is refracted as it moves from the medium of air into the medium of water. Therefore, in applying Snell's law, we recognize that the index of refraction of air is 1.0. Theta 1 is the 28.07 from the previous calculation. Once we enter the water, we have an index of refraction 1.33, and the unknown angle is the angle of refraction, known as theta 2. We can solve the previous equation for theta 2, and plugging in the numbers, we get 20.72 degrees. We recognize that this answer is sensible because we know that the light ray will be closest to the normal in the medium with the highest index of refraction. Since the water has the highest index of refraction, that leads us to expect theta 2 is less than theta 1, and indeed it is. Finally, for our last calculation, we return again to the figure, and we see that drawing a right triangle here, this right triangle includes the angles theta 2, x, and a side whose length is still 15 centimeters. Therefore, we recognize that the tangent of theta 2 is equal to x over 15 centimeters. And so plugging in the value of theta 2 that we had from the previous part of the problem, we get the result of 5.67 centimeters for x, and that completes our Snell's law analysis of the light ray entering the glass of water.